Hi everyone, my name is Zixian. In this talk, I'm going to show you a normal methodology we developed to help us better understand the cost of garbage collection. We apply our methodology on some production garbage collectors. The results are quite surprising, and they might challenge what you have heard about the cost of GC. This was joint work with Steve Blackburn, Mike Bond, and Martin Maas. So, what is garbage collection, or GC? In programming languages with GC, programmers don't need to perform manual error-prone memory management. GC provides automatic memory management, and it works by identifying reachable objects and reclaiming unreachable ones to make more usable memory available. Almost all modern programming languages have GC, and you can find it nearly everywhere. On your browsers, you have various JavaScript engines. On servers, many widely used web services are powered by languages such as Java, C#, Ruby, or PHP. You can even find GC in your pocket on platforms such as the Android runtime. One of the many reasons that programming languages with GC become so popular is that GC provides productivity and memory safety. Programmers are more productive because they don't need to reason about the lifetime of objects anymore. GC also improves memory safety and helps us avoid security vulnerabilities such as use after free or double free. Since the first few GC algorithms such as reference counting and mark sweep invented in 1960, we seem to have been making great strides, and GC is becoming ever cheaper. Now we got sub-millisecond pauses, great improvement in heuristics, and many different algorithms to choose from based on what you need. If our takeaway from all this news is that GC is a solved problem, then if you are a programmer, you should stop worrying about GC costs and embrace the productivity and memory safety that GC provides. If you are designing or implementing programming languages, you should stop wasting time on improving GC because they will only give diminishing return. Go work on the compiler instead. And if you are an architect, since software GC is already so good and cheap, there is no need to improve, for example, caches or memory technology for GC. But is that really so? To answer this question, we need to know about the absolute cost of GC and compare that cost with the rest of the system. However, this is not an easy question to answer. Suppose you have 3 different GC algorithms and you can easily just take them, run an application, and measure the total costs. But there is no easy way to find out how much GC costs. Let's try to tease out the GC cost from the total cost. A straightforward approach is to figure out when a GC starts and ends. And we mark all the costs during GC time in yellow. And the rest is just application. Simple, right? So at the top, we have this very simple GC. Every time the heap is full, the GC has to traverse the entire heap, so you see 2 long yellow blocks. In the middle, we have an improvement, a generational GC. You can collect a subset of heap at a time, so each GC is much quicker. But since you don't clean up as much memory, you have to do more GC. Finally, we have no GC. It's not very practical. It only allocates memory but doesn't do any GC, so you see no yellow chunks as expected. Are we done? Are the yellow blocks the GC costs we want to know? Unfortunately, the reality is a lot more nuanced. Can you notice anything different on this slide compared with the previous slide? They basically look the same. You're right, the only difference is that now each row is covered by a very subtle yellow overlay. They represent the GC costs that are very hard to separate from the application. Why is it so? For example, depending on the GC algorithm, different logic is required to figure out where free memory is to allocate new objects. You might also have barriers, which are code snippets to mediate heap access to help GC monitor changes to the heap. Allocation sequences and barriers are often aggressively inlined into the application code by optimizing compilers, and it is incredibly hard to separate the costs from the application. Apart from these direct costs, GC can also have indirect costs. For example, after the GC finishes, application will resume with a code cache, and that slows things down. GC can also bring indirect benefit. For example, GC can move objects around to reduce heap fragmentation and improves the spatial locality of the application. Things get even trickier when a GC runs concurrently with the application because of the contention of hardware resources and so on. But what if we knew the ideal cost to run an application that includes the potential benefits the best GC can bring but exclude all the GC costs? Then we can simply subtract this ideal cost from the total cost, and the difference will be the GC cost of each collector. Of course, we don't know this ideal cost, otherwise I won't be giving this talk. Fortunately, we can approximate this ideal application cost. We call this methodology distillation. Just like when you have a mixture of different liquid and you want to remove one, you distill the mixture. The total execution cost is a mixture of GC and application cost, and we are trying to remove as much GC cost as possible. So how do we do that? First, we measure the performance just like before, and subtract the explicit GC costs, the yellow blocks we saw before. We remove these explicit GC costs from the total cost. And what remains, no, it's not spirits, but what we call distilled application costs. This distillation is not perfect. As you can see, we still have the yellow overlay on top of the blues. They are only approximations of the ideal cost and are always larger. We choose the best of these as our baseline because it best approximates the ideal cost, and we call it the minimum distilled application cost. Note that the GC that achieves this minimum can vary depending on the benchmark. We then compare the total cost of each GC with this baseline. We subtract the baseline from the total cost, and boom, the difference, these red blocks, is what we call the lower bound overhead, LBO or elbow. It is an empirical lower bound on the cost of each collector, because the costs measured this way are smaller than the real GC cost. A nice thing about this methodology is that it is very simple and can be easily applied to different programming languages, and the distillation process is orthogonal to the cost metrics we care about. You can measure work clock time, CPU cycles, or energy consumptions, and so on. It is important to note that elbow is not the same as normalizing to the best GC or to no GC. A simple normalization, as shown in the right, only tells you how different GCs compare. However, on the left, elbow reviews the GC cost, even including the cost of no GC due to its bad locality. So, we apply this methodology to the production garbage collectors in OpenJDK 17, the latest long-term support release. Let's look at how these collectors fare. First, we measure the overhead in terms of work clock time. Because fundamentally GC is a space-time trade-off, we show the overhead in different heap sizes, relative to the minimum heap size required for a benchmark to run. So towards the left, we have a fairly tight heap, only 1 or 2 times the minimum, while towards the right, we have a very generous heap that is 6 times the minimum. The number here are the elbows. Say if you have an elbow of 1.2, that means you're spending at least 20% more, in this case time, in GC relative to the ideal application cost. And of course, smaller overhead is better. Here, we look at 3 older collectors in JDK, Serial, Parallel, and G1. As you can see along the curves, they all have different trade-offs. The overhead of all 3 collectors are pretty big when the heap is very small, but quickly drops down to around 20% for 2x heaps and tapers off to below 10%. But what about the new collectors? You know, the sub-millisecond pause ones you have seen in the news. Unfortunately, not great news for them. Here we have Shenandoah and ZGC in orange and red. For the smallest heap sizes, their overheads are so big that you can't even see them in the graph. For what is visible, the overhead of the new collectors are well above their older counterparts. As I mentioned before, our methodology is independent of the cost metric used, so let's take a look at another metric. This time, CPU cycles. As you can see, again, different collectors demonstrate different trade-offs. You can see serial showing black, despite being a very simple collector, performs the best this time. It does all GC work using a single thread, so it avoids the synchronization overhead that other collectors have to pay. Overall, you can see this clear distinction between two groups of collectors: the old ones, serial, parallel, and G1, and the new ones, Shenandoah and ZGC. If we look at the year each of these collectors was introduced into OpenJDK, it is alarming. We are going backwards. The newer the collectors, the higher the overhead. There's more. If you look at these two metrics side by side, it reveals some crucial trade-offs that you can't see in a single metric. For example, you can see that around 4x heap size, ZGC's cycle overhead is out of frame, about 50%. But this cost is hidden by parallelism, and ZGC's time overhead at the same size is only about 35%. You might ask, why is this a big deal? Well, a collector that uses many threads in the background burns many CPU cycles. This not only increases the energy consumption, but also leads to opportunity cost, because you could have saved some cycles and run other applications on the same machine. By now, I think everyone can see GC is by no means a solved problem, and we as a community still have a lot to do. You might also wonder, sure, these new collectors are costly, but don't they have sub-millisecond pauses? At least they should be good for latency-sensitive application. So let's take a look at that as well. Let's first see whether they deliver the low pause promise. Here we look at the cumulative distribution of the GC pause time running the Lucene benchmark using a fairly generous 3x heap. Lucene is a search engine executing many queries, and the latency matters because if you type something into a search box, you want the results to return quickly. Note that y-axis is the pause time in milliseconds in log scale. GC pause time are when the application is interrupted by the GC. The new collectors such as ZGC and Shenandoah try to make the interruption short by doing most of the work concurrently with the application. The x-axis is a percentile in log scale as well. For example, the 90th percentile tells you that 90% of the pause time are below the corresponding y value. You can see that the pause time of ZGC is pretty good. It's well below all competitors, and the growth is very modest even towards the tail end. So yes, ZGC does deliver the sub-millisecond pause promise. What about Shenandoah? Unfortunately, it only has low pause time before the 99th percentile, and it's even worse than G1 after that. So it's quite a mixed picture here, and it's getting worse. As you can see in a second, having low pause doesn't actually mean anything. Here, we have query latency as reported by Lucene, and that's what we ultimately care about. We use meter latency to include the latency due to queuing, which is often overlooked. Both x and y-axis are in log scale as before, and again, for query latency, lower the better. ZGC and Shenandoah actually perform the worst out of the collectors tested. In fact, even worse than serial and parallel, which has no concurrency and have to stop the application to perform GC. These results might come as a surprise to many people, but it shouldn't surprise you after you have seen the time and cycle overhead these collectors have. The overhead also affects latency. Even if the application isn't interrupted much by GC pauses, if they run super slowly, the latency is not going to be great. So it is important to measure latency instead of pauses when targeting latency critical applications. So what's the takeaway? First, using our distillation methodology, we can clearly see that GC costs remain a huge concern. Fundamental trade-offs made by different GC can go unnoticed when you only evaluate them using limited metrics. we recommend using more metrics, including CPU cycles, work clock time, application latency, and so on in the evaluation. The silver lining is that there are great opportunities for future research. GC designers and implementers can aim to deliver true low latency GC as opposed to just having low pauses, and do so with low costs in a wide range of metrics. And architectural support of GC can be something worth exploring to lower the cost of GC. Thank you.